we want to define a transformation phi acting on a matrix A as the 0, 1, 0, 0 matrix times A. And we're looking for the kernel of this transformation. Okay, so a couple of things that we need to sort of decide on first. A must be, if we're multiplying by a 2 by 2 matrix, it's got to be 2 by n. 2 rows, as many columns as we'd like. And since the kernel is going to map to the 0, we'll just do this by example. If we take our 0, 0, 1, 0 matrix, and we multiply by, we'll just go 2 by 3 just for an example. The resulting matrix has to be 2 by n, so in this case 2 by 3. So now we've done an example that's 2 by 2 times 2 by 3, but don't get this confused. A is 2 by n. So this could be any n. And the same analysis is going to have to hold. Okay. Now, if we perform this multiplication, we end up with the matrix. 0 times A is 0. 1 times D is D. 0 times B is 0. 1 times E is E. 0 times C is 0. 1 times F is F. And then we're going to have A times 0, 0 times D. You can see pretty quickly that this is all going to be zeros on the bottom. And this is equal, again, because we're looking for the kernel. So the set of things that map to 0, the transformation looks like this, and because we're looking for the set of things that map to 0, we set it equal to 0. And so what we notice here is that D, E, F are the only things that we need to worry about. Those each have to be 0. That's the bottom row here. Now we notice that this matrix had to be 2 by n. So 2 rows, n columns, this could be as many columns as we want, but that second row then has to always be 0. So if we think about this just in terms of words, it's got to be 2 by n matrices with row 2 all zeros. Which means the kernel of this transformation has to be the set of matrices A. These matrices have to be 2 by n, where A to J, so row 2, any column we want, equals 0 for every J. I probably shouldn't have done set notation inside set notation, but you get the idea here. So for any integer j up to n, the second row jth entry has to be 0.